to statics video number 8. On video number 7, I talked about the ideas in section 2.4, which have to do with three-dimensional forces. And so on this video, I'm going to solve some problems. Now, these will help you with your homework and also prepare you for the quiz and for the exam. So these are all really important, and I hope you'll contact me if you have any questions about my work. I'll try to be very methodical, so hopefully it will follow smoothly. But if it is difficult for you, because this is very difficult material, please make sure that you contact me either by email or by stopping by my office so that we can work on it together. All right, so having said that, the first thing I'm going to do is go over here to the document camera, and I'm going to work out some problems from your homework. The first one I would like to work out is problem 2.71, and your homework will be 2.72, which, as you see, uses the same diagram. So these two problems are going to be very, very similar. 271 asks me to determine the x, y, and z components of the 600 Newton force, and then to determine the angles theta x, theta y, and theta z that the force forms with the coordinate axes. Now, as you notice, when I talked last time, we were talking about theta being with axes and phi being with a plane. So what we can see here is that this 600 Newton force makes a 25-degree angle with the y-axis. It then makes the 90 minus 25 or 65-degree angle with the horizontal, the xz plane. And in this case, usually our axes are oriented x, y with z coming out of the board. So that means that the xz plane is not the vertical plane, but the horizontal plane. It's the floor of this. If we were to draw a box, the xz plane would be in the floor of the box. So we're going to start with that idea, and we're going to get our components. All right, so when I draw this problem, 2.71, I start by drawing my axes, my y and x axes, and then I draw the z-axis. Now, when you're doing your homework, you will be doing the other force, the 450 Newton force, so you'll be able to work with that. I'm not going to draw both of them on here because I only need to talk about the 600 Newton force. We're told that the 600 Newton force makes a 25-degree angle with the y-axis. That means right off the bat that theta y is equal to 25 degrees. However, we're also told that the projection of this force into the xz plane, in other words, this force would be the 600 newtons in the xz plane, that projection makes an angle of 30 degrees with the x-axis. Because the x and z axis are 90 degrees apart, that means that this angle between the projection and the z-axis is going to be 90 minus 30, or 60 degrees. But I first have to determine what that projection is. Now, from the y-axis, it's 25 degrees, so that means that down to the floor of the box, down to the xz plane, is going to be 90 minus 25, or 65 degrees. So at that point, I can say that my projection into the xz plane, so that would be the force into the xz plane, is equal to 600 newtons times the cosine of 65 degrees. That's going to get me this component of the force in the floor of my coordinate system. So if I take a cosine of 65 degrees and I multiply that number by 600, I find that that projection is 253.57 newtons. Okay, now I'm going to redraw the xz plane. And what I have is this force. It's a component, but in 2 dimensions it looks like a full-on force, has a magnitude of 253.57 newtons. And we've been told that this angle between the x-axis and the projection is 30 degrees. And we know that since the x and the z-axis are 90 degrees apart, that this is 60 degrees. So what that tells me is that my f sub x, that projection purely onto the x-axis, is equal to 253.57 newtons times, because this is adjacent, the cosine of 30 degrees. So if I type in cosine 30 degrees in my calculator and multiply it by the projection, sorry, that was wrong, cosine 30, multiply that, 0.866 by 2, boy, my fumble fingers today, cosine 30 equals times 253.57 newtons is 219.59860 newtons. So my Fx, I've got it to an axis now, is 219.60 newtons. And that means that my F sub y is going to be 253.57 times the, I could say the sine of 30, or I could say the cosine of 60. So this is my F sub y, 253.57 times the cosine of 60 degrees. So if I do those numbers, I get 60, cosine 60 times 253.57, and that component is 126.785 newtons. All right, so now I know some interesting things. I know that my, I still need to find my F, this is my F sub z, pardon me. I need to find my F sub y, which, because I knew this angle was 25 to begin with, is going to be 600 newtons times the cosine of 25 degrees. So the magnitude of that is 25 times 600, 543.784. All right, so now I have my F sub x component, my F sub y component, F sub z component, and my F sub y component. If you remember my directional cosines, theta x, I know, is equal to my component in the x direction divided by the entire force, the resultant. So in other words, here I would have 219.6 newtons divided by 600 newtons. And since I have newtons on top, newtons on bottoms, the units go away, which is important for directional cosine. Cosines are dimensionless. So this value is 0.366. Theta y is going to be equal to F sub y over F. My F sub y is 543.78 divided by 600 again, both in newtons. So if I take 543.78 and divide it by 600 equals 0.9063, right? All right, now we also know that this should be the cosine of that angle, cosine of 25. So if I take the inverse cosine of that, do I get 25 degrees? Yes, I do. So everything checks out. My theta z would be F sub z over F. My F sub z is 126.785 newtons. My F is 600. So if I take 126.785 and divide by 600, I get a directional cosine of 0.211. All right, so the questions then are determine the x, y, and z components of the force, which I have right here, and then it asks me for the angles. Well, I have the cosines of these angles, so to find the angle themselves, I need to take the inverse cosine of each of those numbers. So theta x, if I say second inverse cosine of 0.366, this is theta x equals 68.5 degrees. Theta y, we've already determined, is 25 degrees, and we checked it. And theta z is going to be the inverse cosine of 0.211. And so that angle is 77.8 degrees. All right, so we have all of our answers for the first problem. All right, the next problem I would like to work is 277. And 277 in your textbook says we have a cable AB and it is 65 feet long. So we're looking at AB. And we're told that the length of that cable is 65 feet and the tension is 3,900 pounds. So we want to determine the X, Y, and Z components of the force exerted by the cable on the anchor at B. Okay, so in other words, the cable is pulling the anchor up, right? It's not pushing down on the anchor, it's pulling up. So the direction of my sign is from, or the direction of my force is from B to A, and then I want to find the angles defining that direction. Theta x, theta y, theta z. All right, so once again, this time I'm drawing my coordinate system a little slanted just to accommodate this picture a little bit better. My transmission power goes from point 0 to point A, and my anchor is here at B, behind the x-axis, and so we're going from B to A. Well, the first thing that we can see is that the angle, let me get a different color pen, from the x-axis to B, we're told that that angle from B is 20 degrees. And we are further told oh, that's not the problem I chose. I don't know what I was thinking of. Oh, there it is, 77. There it is. Okay. So, sorry, I'll go ahead. We're told that the tension in this cable, the magnitude of the tension, is 3,900 pounds. And we are told that the distance from the x-axis to point A, if we extended this back, okay, or in other words, how tall this is from A down to the ground is 56 feet. So we have some of the geometry, don't we? We're further told that this cable is 65 feet long. Okay, so I've got everything written down. Okay, so determine the X, Y, and Z components of the force. So we want the tension in the X direction, the tension in the Y direction, and the tension in the Z direction. And we further want the angles theta X, theta Y, and theta Z. All right. Well, what we're talking about here is if we take this cable and we project it down into the XZ plane, that this projection forms an angle of 20 degrees with the x-axis. But what is this angle? In other words, what are we going to have to do to project this 3,900 pound force into the XZ plane? Well, the answer to that can be seen not by the force triangle, but by the triangle, the geometry of the location of this angle, and what we have is our y component is 56 feet long, and our hypotenuse, or the overall length, is 65 feet long. So we can find this angle, in other words, theta y, because we have the hypotenuse and the adjacent. So it's equal to the inverse cosine of the adjacent side length over the hypotenuse length. And so if I take that measurement, 56, divide by 65, and I take the inverse cosine of that number, I find that this angle is 30.5 degrees. All right, well, if it's a 30.5 degree angle with the y-axis, it means that the angle that it makes here with the xz plane is going to be 90 degrees minus 30.5 degrees, or 59.5 degrees. All right, so now what I can do is I can take this tension and find the value of the tension in the xz plane. The tension in the xz plane then is going to be the magnitude of the tension, 3,900 pounds, times the cosine of 59.5 degrees. And cosine of that number is 0.5 something, multiply that by 3,900, and so the tension in the xz plane is equal to 1,980 pounds. Now what about the tension in the y direction? Now this is on a plane, this is just on an axis. Well, we know that angle is 30.5 degrees, so it's also adjacent, so 3,900 pounds times the cosine of 30.5 degrees. Cosine 30.5 equals times 3,900 equals, so the tension in the y direction is equal to 33,360.35 pounds. Okay, now I've got this projection, and I need to recognize that in the xz plane, it's going to be a little bit different here, but let's go ahead and draw this. We have this force going backward, and its magnitude is 1,980. What that means is that the direction is negative in the z, or the magnitude is negative, not the magnitude, but the direction is negative in the z sense. We're also told that this angle is 20 degrees. So if we drop this down, we can say F in the x direction is equal to 1980 pounds times the cosine of 20 degrees. So if I do cosine of 20, multiply that by 1,980, we get 1,860.6 pounds. So I call that, I kind of switched my variables here. I should refer to this as T sub x, because we're talking about a tension. And then what about in the z direction? Well, there's a couple of different ways we can think about it. We can think about it as being negative times the cosine of 70 degrees, because 20 plus 70 is 90. Or we can think about it as being the cosine of 90 plus 20, which is 110. So let's just check out those numbers. Cosine of 110 is negative 0.34, and the cosine of 20, oh, excuse me, this is in the z direction. There's my cosine. This would be 70. Okay, the cosine of 70 should just be the positive of that number, right? So either way, if you draw your picture, the trig is going to correspond correctly. All right, so in the z direction then, the tension in the z direction is equal to, and it doesn't matter which way I want to think about it, 1980 times let's just do, since we're doing cosines, cosine of 110 degrees, which is 90 plus 20. And so if I do cosine 110, I just did that, but that's a negative 0.342. Multiply that by 1980 equals negative 677.2 pounds. All right, so to fill in my answers to begin with, my T sub x is 1,860.6 pounds. My T sub y is 3,360.35 pounds. And my T sub z is negative 677.2 pounds. All right. Now, if you think about this, if we go from point B to point A, we're going up. So this should be positive. But when we go from point B to point A, we're moving to the left. So this would actually be a negative, and then we're actually moving forward because this is at 0 and this is behind. So to get our signs to correspond to the diagram, we need to think about where we start and where we finish. So B to A is up, but B to A is to the left, so that's negative, and B to A is forward, so this is positive. Okay? So now how do we find our thetas? Well, we know that the cosine of theta x is equal to T sub x over T, which is negative 1860.6 pounds over the entire tension, which is 3,900 pounds, or the cosine of theta x is 1860.6 with a negative sign, divided by 3,900. Let's go ahead and do this. 1860.6 negative. It didn't do that. Negative 1860.6 divided by 3,900 equals. So this value is 0.477. So that means that theta x is the inverse cosine of negative 0.477, or second inverse, second answer. That number is 118 degrees, 118 and a half. Similarly, theta y is going to be the inverse cosine of 3360.35 over 3,900, which is divided by 3,900. Take the second inverse cosine of that, and that angle is 30.5 degrees, which we found right there, and theta z is the inverse cosine of 677.2 over 3,900, which is second cosine, second answer. That number is 80.00 degrees. All right, and so those are your answers for problem number 2.77, which is going to be very similar to the homework problem I've assigned of 2.78. Now, I would also, I've assigned problem 2.90 for homework. So 2.89 is going to be very similar, and I'm not going to have time to do the entire problem, so I'm going to do a partial setup of this. So it says a rectangular plate is supported by 3 cables. Knowing that the tension in cable AB is 408, determine the components of the force on the plate at B. All right, so once again, I do not have to draw the whole picture, but I have O to A, and I have A to B, and it's the tension of the cable on the plate. So the cable is pulling the plate up. All right, now this is a little bit different. We do know that this tension is 408 newtons. But we don't have anything else about the forces. We have other things about the dimensions. So in other words, we're really looking for what's going on from point A to point B. So let's look, or excuse me, I should say it backward, from point B to point A. So let's look here. The dimensions are in millimeters, but B is at a negative value of 320 millimeters in the x direction, and A is at 0. So that means from B to A, the distance in the x direction, is from B to A is equal to 320 millimeters. The distance in the y direction from B to A is up. The distance from B to A in the y direction is up a total of 480 millimeters. And in the z direction, from B to A, the z direction goes back into the board, and you see it goes from 360 back to 0, or in other words, it's equal to a negative 360 millimeters. All right, so the process, I'm going to finish up in just a minute here. You need to find the length using a three-dimensional Pythagorean theorem. So you take the square root of the sum of the square of all of those factors, and then you can find your directional cosines based on the distance in each direction divided by the total length. Take the inverse cosine of those to find, this should be the cosine, sorry, the inverse cosine of that to find the angle, the theta x, theta y, and theta z. And then you can multiply by each of those to find the component of the tension in the x direction. So in other words, the component of the tension in the x direction is the tension times the directional cosine in the x direction, and similar. All right, everybody, so please let me know if you have any questions about this, and we will talk about it in class and do the homework, give the homework a try, and then if you're not able to do it, make sure you get a hold of me. Thanks.